Hello and welcome to the C programming lecture on memory allocation and releasing. So memory management. Most of the time particular languages of today are managed languages. What this means is that the underlying implementation of the language, there are particular pieces of running processes that actually manage the memory allocation and releasing for you. Typically, these are called managed languages. They have something called a runtime associated with it that adds overhead. So in C, every bit of memory can be managed by the programmer. Therefore, it is the job of the programmer to manage the memory. So it may sound a little bit scary to quote unquote manage memory, but it's really nothing to be afraid of, and it actually helps you understand how computers work more than using a managed language. So programming, so let's talk about like the different loading and memory segmentations of a program. So when a program is launched, the binary data that represents a program needs to actually be loaded into RAM. So this memory is segregated into different chunks. Typically, you'll have like a high address and a low address, and then you have these different segments here, oftentimes referred to as a stack and a heap. And then you have other segments towards the lower end of the address range that are uninitialized data, initialized data, and a segment called the text segment. So normally you'll hear people say the stack grows downwards and the heap grows up. This is typically what they're referring to as you see the up and down arrows, and they're usually referencing the address range. So your particular program will have a chunk of memory assigned to it just by default as the program, and this is generally a higher level overview of what it will look like. Okay, so the program stack. When a program is executed, the running process contains its own stack of memory. The stack is considered a transient storage of local variables during the program execution. So in other words, a stack is used for short-term variable storage, so local scope stuff. The entire time we've been using the stack inside of our programs, we haven't actually requested for other chunks of data to be returned from us. So sometimes our programs will become too large to use the stack. So we will need to actually ask the operating system for additional memory. So typically the compilers will have a default stack size. So you can actually increase the default stack size, but normally you don't necessarily need to do those things, especially at this particular point in your programming career. As I think this goes without saying, as more variables are placed on the stack, the address of those variables will be at a lower memory address range, is what we saw in the last slide. Like, so it grows downward. So it increases as the amount of variables increase that we use, it will start taking downward towards the lower memory address range. Okay, program heap. In programming, it's common to want to keep around data for a longer period of time than using it within a local function or something else of that nature. So there are alternatives to that. We could create global variables, so pulling a variable out and keeping it in a text segment or of the actual program. It becomes some type of global variable that you can access from anywhere. However, sometimes you just want to be able to request a chunk of memory and use that chunk wherever you'd like. So in C, there's a function actually called malloc. So this is memory allocation that we request from the operating system. So this memory that we requested from the operating system is considered to be heap memory. Now, the lifetime of this memory is persistent. It is not transient, so it's not temporary. Temporary in the sense of the lifespan of the program. It's temporary in that of when the program terminates, the memory will be released. However, if the process keeps running, if the program keeps running, that storage, unless a function which is named free is called, that particular memory address, that particular block of memory will always be in use until it is quote unquote freed. So the definitions for both functions that I mentioned, the malloc and the free function, are located in the std lib.h header. So using malloc, the function malloc is defined within the std lib header. It allocates a region of memory large enough to hold an object whose size by a byte passed in. The return value of the function is actually a pointer to the first element in that region that you requested. So whatever block size you requested, again, it's usually in bytes. It's guaranteed to be properly aligned for any data type as well. So the return type is typically a void pointer. Therefore, you'll need to cast that. So that was important to learn casting. We'll need to recast that to the appropriate type that we want. So if the system, for some reason, cannot allocate this memory, the function will return a null pointer. So just be aware of that. If it cannot allocate, it's always good to check to see if the pointer returned is null or not. And if it is null, then you can just assume that there is some other problem going on. So the allocated memory will live in the program's heap space until the function free is called. This is something we mentioned previously, or the program has exited. In other words, when a program's entry point has returned, the allocated memory will actually be released back. So oftentimes y'all hear other words like memory leaks and stuff like that. What a memory leak is when the duration of the program is running, additional resources are constantly requested but never released. So you have a memory leak in this program. So here's a heap allocation example. So what we are doing here is we are calling the malloc function on line 7. So we declare a variable, stack variable, which is 10, and we have a heap variable, which is on line 7. We actually request from malloc and we recast, you can see here, to an int pointer. We say, give me a block of memory that is the size of an integer, so 4 bytes. It gives it to me. I can print that. I can actually deref and assign a value to it, and I can print both of these variables at. So you can you can see that the stack variable address is at some arbitrary address, but then our actual heap address is at a very, very different, not even near, really near this other address. It's pretty far away. So we can see that this variable here is what this value of this heap variable is what we assigned it on line 8. Okay, so using free. The free function deallocates a region of memory previously allocated to malloc or some similar function. The argument passed to free must be a pointer that is the same pointer returned to by an allocation function. So meaning when you allocate, that pointer variable needs to match up to some particular free, like that memory address needs to match something that was returned from malloc. Once the region of memory has been freed, it should not be used again for any other purpose. The use of this pointer, that is considered a quote-unquote dangling pointer, will have a unpredictable effect. So again, like that memory address, think of it as like clearing it out and then, you know, moving on. Now, underneath the implementation of malloc, the reason why they say this is because the function malloc and free, the way that they operate internally, it doesn't mean that they actually have to release the memory back into the operating system for additional uses. Like that could be very inefficient to constantly do. So what would happen, what could potentially happen instead, is that they put it back inside of a free pool or something for you to then, whenever another malloc occurs, they can reuse that address for something else. Now, I'm not saying that's exactly how it works, but that is the reason why they consider this an unpredictable effect. So here's an example of a heap allocation and deallocation. Again, we are doing basically the same exact thing as the last example, except for right here on line 16, we are actually freeing that variable. So we can see here after we, again, lines 6 through 13, 14 technically, are basically the same thing as our prior example, but you see that I free the variable and then I try to reprint on line 17 our heap variable again. So that's two outputs which are the same, and then our next after free is using that same address, but you can see that after we freed it, this is what I said is almost actually happening here, is that when we deref it and we actually print out the variable address plus the value, all it did was zero out the value when we called free. So that it didn't actually cause a crash for dereferencing because technically that region of memory was still readable and writable. So we could possibly write into that again and then dereference it and have it come out with some another crazy value. Now, that being said, none of this functionality is guaranteed. Again, we don't know the internals of how this works. I mean, we could dig into it and figure it out, but there's really no need. You shouldn't even be doing stuff like this in the first place. I just wanted to show you what it looks like. So again, here is the variable that, here's an even crazier example. So on line 20, we have another heap variable. We actually request from malloc another size of an integer. Right, so we say, okay, give me a new int. It returns a new block of memory. That block of memory is then assigned to the value 300, and then we print out our variable 2. And we can see that's exactly what we expect. However, if you notice, the address that it points to was actually our prior heap variable address. So when we reprint it out, it has actually 300. So you could see this is almost exactly the behavior that I said was happening before. Is that when we freed the memory, it was put back into a pool of available memory. And then when we re-requested from malloc to give us another block of memory, it said, hey, this was previously freed. This is up for grabs. But that dangling pointer from heap variable, heap underscore variable, not heap underscore variable 2, the original one on line 7, that actually points to the address, which is now heap variable underscore 2. So we have a dangling pointer. So this is a perfect example of exactly what I was referring to in the last slide. Okay, so virtual memory. Now, I don't want to get too far into the weeds here, but I think it's useful, especially for beginners, to understand some of this stuff at a high level. So modern operating systems implement something called virtual memory. At a high level, virtual memory is just basically a lookup table that maps to physical memory. So, you know, when we're talking about these addresses, what we're really referring to is a virtual address. So there's other problems associated with this. And the reason why we do this is basically because sometimes it doesn't make sense, especially a program that may be not running as frequently, to constantly hog up a large block of random access memory or RAM. So typically that stuff will be offloaded on the disk if it's not requested frequently, and whenever it's requested again, the stuff that was offloaded on the disk is actually loaded back into RAM, and it just kind of trickles down through this whole process. So usually that's referred to as something called like a page fault. So whenever it tries to access something that's not addressed to RAM, we have to go out to the disk and load it in. So again, what this means is that the data being requested is on another type of storage device. In this case, we're just saying a hard drive or a solid state drive, and it needs to be pulled off that particular device and loaded into memory in order to be able to run that particular program. So again, a high level overview of what is of memory access using virtual memory. So here's our RAM, and here is our virtual memory table, and here is our hard drive or SSD, some alternative storage. So we can see here that this particular address is mapping into this slot here, into address 1. And let's say we only have 3 blocks of RAM for whatever that means in this context. And we can see that actually our virtual memory address of 4 points to 2, and maybe 2 is on the hard drive, 5 is over here. And you can see that this can kind of get like an unwieldy process. It gets a little crazy, but you know, this is a general overview of how it could potentially work and how things can get a little confusing. Now, there's a lot more to this. This is, again, a very high level overview, but just keep this in the back of your mind. And if you want to do further research into it, definitely look into this. So memory access times. So a clock cycle is defined by the speed of a computer processor. So when you hear things like 3.2 gigahertz, okay, what does that mean? Well, that's actually 3.2 billion cycles per second. So modern CPUs are typically bottlenecked by main memory access times. So we clever people invented things called CPU caches. So we have CPU caches in order to reduce the need to reach out to main memory to reduce the overall access time. So this is just high level details for you to just have more intuitive knowledge of how these particular things work. So I want to show you, just again, this is just made to draw a point for you to consider rather than give you hard numerical evidence. So let's say in this diagram that we have a CPU, and in the CPU we have a physical 4-core system. And with each of these cores, we have a level 1 cache, a level 2 cache, and a globally shared level 3 cache. So what occurs here is that each processor, each core, has its own L1 and L2 cache, and they all share this L3 cache. So here is RAM, and then RAM, let's say, attaches to some storage device. To just give you an idea of how many cycles it takes your processor to access L1 cache, let's say it's about 4 cycles, okay? And then we can just say, okay, well, to reach L2 cache, because L1's at a lower layer than L2, L1's, first of all, L1's going to be a smaller size than L2, and that's why these things have lower storage amounts. If you ever see the specs on a CPU, L1 will be smaller than L2, L2 will be smaller than L3, and your L3 will always be smaller than your actual physical RAM. So anyways, you can see the access time for L2 approximately 11 cycles. L3, substantially larger, is approximately 39 cycles, but RAM in and of itself is approximately 200 cycles, much slower. So imagine that, or imagine going out to disk, how much slower that would be. That's orders of magnitude slower, even more so than RAM versus L1. Now, that being said, there's also even more crazy stuff. Again, this is the high level overview. There's all types of problems that could happen when you're just trying to fetch like interop in between cores that need to share data. There's all kinds of insane stuff that can happen. So again, this is the graph. So here's our basic, our fictitious CPU with our fictitious RAM, and here are the fictitious cache sizes, showing that like L1's smallest, L2's like smaller than L3, and so on and so forth. So again, a brief review of what we kind of covered in this lecture. So programs have segmented memory. Programmers are usually interested in the stack and the heap regions of a particular program. Virtual memory abstracts the idea of physical memory in order to create a level of indirection to potentially offload idle processes to a storage device instead of physical memory. So again, like this actually allows you to have more programs running and than what you can actually store inside of your actual physical RAM. So heap allocations allow the programmer to reserve memory when needed and free back whenever it's not needed. CPU main memory access times are slow. So CPU caches were created in order to reduce the need to frequently reach out to main memory. Now, there's all types of things that we can get into regarding this. I just wanted to give you a very brief overview of what it means, what a CPU cache is. I'm sure that if you're taking this course, you either already know or you have seen it when looking at your computer specs. You've probably seen something like the term L1 cache, L2 cache, L3 cache. So just to give you a context of what those things are used for, there's all types of information that is great about CPU caches. So let's go ahead and just mess around with some of this stuff in code. All right, let's go ahead and start a code example here about memory allocation and releasing. So again, we're just going to go through creating our basic program here for just making sure all of our tooling is set up. So in this particular case, we're going to use the stdlib.h header. So I'm just going to go ahead and include it now, even though we're not going to be using it inside of our hello world example. Again, this is just to get into a habit of making sure that all of your tooling is working, all of your command line, your the code execution, all that stuff. So all right, we're good. This appears to be working just as we expect. So let's start out with the simplest case here. So what I want to do is let's just start out with a character pointer, right? So we'll just do one character at this particular point in time, so null. And we'll say that our character pointer, let's say that it's, let's just do an allocation. So remember that these are strings, right? So in this particular case, we're just gonna use a string as a easy example. So let's start with 2 characters, and now what we'll do is we'll say s is going to be equal to a character pointer. We're going to ask for a particular amount of memory, and in this case we're going to say we want 2 times the size of a character, right? So because we want 2 characters, so an array technically. Remember when we said that arrays are technically pointers? Well, it turns out that, you know, this character pointer is what we're referring to here. All right, so now we've requested that. What we can do is we can check to make sure that if s does not equal null, then that's good. Then we can do stuff with this. So if it doesn't equal null, what we want to do is let's go ahead and assign the first one to, we've been using exclamation point. I like that one. Let's just use exclamation point. And now, as always, we need to terminate our actual string with a null character here. So this is just going to be a very simple example of what's going on. So we need to dereference this pointer value. We can pass this in %line s, and hopefully we should get the output we expect. Okay, so segmentation fault. Now what's probably occurring here is that we are actually dereferencing the pointer when we didn't actually need to do that in this particular case because of this %line s. But we could see that when we remove that dereference, because it's actually going to do this underneath, the segmentation fault goes away. So we can see that here. So let's go ahead and expand this a bit. Let's say that we have a 10 character buffer maybe. And let's just add some more stuff into here. Let's just say test. And then again, this is the long way to do this. There's other functions that we could use to help us out. Let's just say test. You have a 10 character buffer. Let's say test is good. We'll just put an exclamation point at the end and delete this guy. So this is going to be 0, 1, 2, 3, 4, and 5. So we have a total of actually 6 characters. And what we should see is just test exclamation point and then our null character, which should terminate here. Now, what would happen if I remove this? So let's just put it 2 exclamation points. Interesting. So it actually shows that we are able to, this actually shows us that we're able to, like, a null character is actually occurring after our particular s, 6th element. So what we could do is, because this is a size of 10, it could be returning us a nicely formatted block of code, which is all zeros or null values. So let's go ahead and say we have 1, 2, 3, 4, 5, 6, right? Let's just declare 6 and see what happens. Same thing. Okay, let's shorten it up a bit. Let's say 5. So now, technically, at 1, 2, 3, 4, 5, this is our last one. This is our last index that we were able to access. We're doing a what? A buffer overflow. And it still prints that out. So let's go ahead and erase this. So it looks like it's keeping our memory nicely formatted for us, and we don't necessarily need to worry about what is occurring here. Now, That's not always the case. So we can say, let's do this. Let's loop over each of these instead of printing it out like this, and print out the individual character with the numerical result here. I is less than, we know it's 5, so let's just say 5. Again, this is just for brevity, like we just want to keep it pretty simple. So we'll print the character C, and then we'll just say the C int maybe. So what we're gonna do is say, okay, s of at our I, and then maybe here we say si again, but this needs to be casted to a int pointer. So we expect all of these to be 0. Right. So like that. And then let's see, cast from, we're in a different size. Okay. Let's remove the cast. See what we get. Okay, perfect. So now let's just go ahead and add our first element again. Make sure that we're getting the proper integer value. So this should be 33 for our ASCII chart, and that it is. So we can see that this is actually showing us when we allocate this memory. Let's go ahead and go 10 over, or 5 over in this case. We can see that the contiguous block of memory actually is nicely formatted into a way of, like, what it's doing is actually saying, okay, at this particular element, just like zero out this entire block. But what happens if we go significantly farther? Let's just say 256. Now it's possible that it's all 0, and it does appear to be that way. So somehow, our compiler is smart enough to know to zero out this particular memory address allocation, this block of memory. Now, that's not always going to be the case. It's not necessarily guaranteed. Let's go ahead and let's do this. Let's delete this code. Let's delete this. Let's just use an int x pointer and set it to null. And what we're going to do is say x is equal to an int pointer. We're going to malloc just one integer, which is size of int. And let's just print out x, the value of x right now, and see what it is. Sometimes, depending on the compiler that you're using, like I said, it will initialize it to 0, and sometimes it will be garbage. So in this particular case, it's definitely garbage. But like, in particular scenarios, maybe because we're using C strings, it knows to zero that out. Different types are going to be handled different ways depending on what is occurring. So, in this particular case, it's going to be some arbitrary value here. So let's go ahead and let's actually do the same thing as before. So we're going to declare 4 integers. So technically it's an array. So we have an array of integers. We a list of contiguous integers. And what we're going to do is we're going to print out just individually each one. Let's just use again a for loop here. We already know it's 4, so we'll just do this, I++. So now what we're going to do is just print out x at some index, right? And then we're just going to print out the value, line I, and then what we're going to do is say at that particular index, right? So we can see that when we are actually requesting a multiple byte size, that it's actually zeroing it out for us, whereas when we were just doing individual elements, it may not have been doing that for us. So let's see. Let's again to show. Let's just hammer away this point hammer home this point here. So we see that this block of memory will keep this allocation, this malloc, and we can write a free here. So we'll free our x here. We'll keep this together, and then what we're going to do is we're going to say, okay, int, again, x pointer, and we're just going to do 1 malloc 4 times the size. Well, we're not going to do 4, we're just going to do the size of int, because we just want 1. And then, oftentimes, this will be some garbage value. That is typically what we're expecting. And you can see that I'm freeing x twice, but freeing x twice in this context doesn't, it's perfectly fine, because the value that this x variable points to is this particular malloc, whereas this one's different. Now we could be using the same memory address, so we could say printf x address, right? So let's do that. It's possible that we are reusing this, and then after we free, you'll see that you know, this will be the same. Well, actually, let's just do malloc, and after we malloc, we'll do this. So you see, may not see it out. And indeed, that's actually what is occurring here. So there's some weirdness actually that's happening right here, and that may just be due to the fact that this is actually needs to be dereferenced. So this should probably be 0 now. Yes. So we could see that this memory address here is actually matches our above one. I noticed that I misspelled address, so let's go ahead and, just for completeness, add this. So we need to actually dereference what we what this variable is. We need to deref the pointer in order to get the value out. Before we were just printing the address, but it is indeed exactly what I said. It's not guaranteed to actually zero out that memory. There's nothing that guarantees that malloc will give you back a block of code that will be completely zeroed out. This is because this is using the same address as something we declared previously. I don't know. Let's you know, it's a good point to just try to test this out. So we set it to null. Let's go ahead and just say x is equal to, again, we'll do this. Let's keep these together. And sometimes this is often the best way to test stuff out to see how it works. Well, let's see. Okay, it's zeroed out, and you can see throughout the rest of the entire program, we're still reusing the same address. So instead of doing all this temporarily, let's delete this code, save, and see if we get a similar result. And we do. So it is in fact zeroing out in this particular case, but like I said, there's nothing guaranteeing that it will be zeroed out. There's a chance that there could have been some, like if we write a bunch of memory into, if we write a bunch of stuff and free it or whatever, there's a chance that the malloc and the free function will not guarantee that the initialized value at that particular memory address should be the default initialized. You know, if it's an integer, it may not give it the value of 0. It may be -1000 or something. And again, this is just to do with, you know, the fact that it's just returning you an address, and sometimes it doesn't care about clearing out that particular memory. But in our use case here, as we've seen, it does appear to be zeroing out whether we're requesting one or multiple integers. So just kind of some food for thought. Hopefully this gave you a little bit of insight into what is going on in using malloc and free.